Hello, I am your host Dimidum. This is my first video, so if you like this, please smash the subscribe button and make it gray for the notification of second video. In this video we were going to talk about dark matter. Dark energy, what its impact on the universe, how much it contains dark matter and dark energy. What it contains, from what it is made of, etc. So let's start the video. So what is a dark matter? By fitting a theoretical model of the composition of the universe to the combined set of cosmological observations, scientists have come up with the composition that we described above: 68% dark energy, 27% dark matter, 5% normal matter. We are much more certain what dark matter is not than we are what it is. First, it is dark, meaning that it is not in the form of stars and planets that we see. Observations show that there is far too little visible matter in the universe to make up the 27% required by the observations. Second, it is not in the form of dark clouds of normal matter, matter made up of particles called baryons. We know this because we would be able to detect baryonic clouds by their absorption of radiation passing through them. Third, dark matter is not antimatter, because we do not see the unique gamma rays that are produced when antimatter annihilates with matter. Finally, we can rule out large galaxy-sized black holes on the basis of how many gravitational lenses we see. High concentrations of matter bend light passing near them from objects further away, but we do not see enough lensing events to suggest that such objects to make up the required 25% dark matter. However, at this point, there are still a few dark matter possibilities that are viable. Baryonic matter could still make up the dark matter if it were all tied up in brown dwarfs or in small, dense chunks of heavy elements. These possibilities are known as massive compact halo objects, or machos. But the most common view is that dark matter is not baryonic at all, but that it is made up of other, more exotic particles like axions or WIMPs, weakly interacting massive particles. So moving on, second topic: what is dark energy? More is unknown than is known. We know how much dark energy there is because we know how it affects the universe's expansion. Other than that, it is a complete mystery. But it is an important mystery. It turns out that roughly 68% of the universe is dark energy. Dark matter makes up about 27%. The rest, everything on Earth, everything ever observed with all of our instruments, all normal matter. Some theorists have named this quintessence, after the fifth element of the Greek philosophers. But, if quintessence is the answer, we still don't know what it is like, what it interacts with, or why it exists. So the mystery continues. A last possibility is that Einstein's theory of gravity is not correct. That would not only affect the expansion of the universe, but it would also affect the way that normal matter in galaxies and clusters of galaxies behaved to come into existence. Then one version of Einstein's gravity theory, the version that contains a cosmological constant, makes a second prediction: empty space can possess its own energy. Because this energy is a property of space itself, it would not be diluted as space expands. As more space comes into existence, more of this energy of space would appear. As a result, this form of energy would cause the universe to expand faster. Unfortunately, no one understands why the cosmological constant should even be there, much less why it would have exactly the right value to cause the observed acceleration of the universe. Calculate how much energy this would give empty space. The answer came out wrong by a lot. The number came out 10,120 times too big. That's a 1 with 120 zeros after it. It's hard to get an answer that bad. So the mystery continues. Some theorists have named this quintessence, after the fifth element of the Greek philosophers. But, if quintessence is the answer, we still don't know what it is like, what it interacts with, or why it exists. So the mystery continues. A last possibility is that Einstein's theory of gravity is not correct. That would not only affect the expansion of the universe, but it would also affect the way that normal matter in galaxies and clusters of galaxies behaved. This fact would provide a way to decide if the solution to the dark energy problem is a new gravity theory or not. We could observe how galaxies come together in clusters. But if it does turn out that a new theory of gravity is needed, what kind of theory would it be? How could it correctly describe the motion of the bodies in the solar system, as Einstein's theory is known to do, and still give us the different prediction for the universe that we need? There are candidate theories, but none are compelling. So the mystery continues. The thing that is needed to decide between dark energy possibilities, a property of space, a new dynamic fluid, or a new theory of gravity, is more data, better data. Transparent. However, dark matter does have mass, which we see by its gravitational influence. Studies of galaxies show stars and gas moving as though there's a lot more mass than we can see pulling them along. Based on the motion of what we can observe, galactic dark matter resides in a halo surrounding the ordinary matter of the galaxy. Astronomers also study dwarf galaxies, which are less bright and therefore harder to observe, but which contain a higher fraction of dark matter than their larger cousins. Galaxy clusters can contain hundreds or thousands of galaxies, each of which have their own dark matter halo. However, the cluster has its own dark matter, which outweighs everything else put together. This dark matter influences how individual galaxies and hot gas move inside the cluster. Astronomers can measure how much invisible mass is inside a cluster by the motion of the visible material, much as they do with galaxies. Researchers can also determine the amount of cluster dark matter by the way its gravity affects light. This effect is called gravitational lensing, and it provides an independent measure of how much mass is in a cluster and where it resides. One particular galaxy cluster, known as the bullet cluster, provides some of the best evidence we have for the existence of dark matter. This cluster is made up of two smaller clusters that collided sometime in the past. During this collision, the hot gas interacted to produce a shock wave, similar to that made by a bullet. However, gravitational lensing shows that most of the mass of the combined cluster is collected around the galaxies, not in the center where the gas is. The hot gas interacted to produce a shock wave, similar to that made by a bullet. However, gravitational lensing shows that most of the mass of the combined cluster is collected around the galaxies, not in the center where the gas is. That provides us with the first independent measurement of how much gas and dark matter are in a galaxy cluster, where in most clusters the plasma and dark matter occupy the same regions. Using fluctuations in the cosmic microwave background, CMB, astronomers determined that dark matter is about 27% of the contents of the universe, in terms of its overall contribution to the total mass and energy content of the cosmos. So that's it. We have to end this video here. In this video we understand what is dark matter, what is dark energy and what its impact on universe. So if you like my content, please share it with your friends and colleagues and like this video.